Hello, today I want to talk to you about alkyne reactions. I know in my section we talked about alkynes a little bit last semester, and in Professor Link's section I'm not sure that you talked much about them at all. So what I want to do is just provide an overview of the important alkyne reactions so that will help you as you think about what you're doing during the review problem sets and thinking about reactions that we're going to see on Monday. So there are three important types of alkyne reactions. We have hydrogenation reactions, where we're adding H2 or the equivalents of H2. We're doing hydration reactions where we're adding water, and then we're going to do alkylation, making carbon-carbon bonds. All right? And the key thing to think about when you're thinking about alkyne reactions is their relation to alkene reactions. Right? So hydrogenation reactions and hydration reactions are very common alkene reactions that we should be familiar with. All right? And we'll see the similarities and differences when we look at alkyne compared to alkene reactions. The alkylation reactions, these are specific to alkynes. They do not happen with alkenes at all. All right? So that's important to think about. What is special about alkynes that enable them to make carbon-carbon bonds where we can't do this with alkenes? All right? So let's look at each of these in turn. So let's start with our hydrogenation reactions. Right? And if we think about the ways that we did hydrogenation with alkenes, right, we can start with an internal alkyne. Right? When we thought about these reactions with alkenes, we said we're going to add H2 with catalytic palladium or platinum, whatever it happened to be, and we would add in a syn fashion H2 to the alkene. Now clearly if we add H2 to the alkyne, we make an alkene, and then the alkene can react further to make an alkane. So what happens is it ends up reacting twice, and we end up getting to the alkane. Right? Very efficient way to go from an alkyne to an alkane. The more interesting thing is if we wanted to stop this reaction at the alkene. Right? If we wanted to do that, we can't use these conditions because we know they react with the alkene. Right? So for example, if we wanted to make this into either the cis alkene or the trans alkene, could we do that? Do we have conditions in which we could do this chemistry and get these alkenes, which are important functional groups that we know how to do reactions with, right? And so getting to the cis alkene, the way we'd want to do that is to add H2, but only one time. And so the reality is we have a catalyst that enables us to do that, right? So this is H2, and it's called Lindlar's catalyst. And Lindlar's catalyst is just a less reactive version of catalytic palladium or catalytic platinum, so that it only reacts with the alkyne and then not react at all with the alkene, right? And again, we're doing, as we talked about in alkene chemistry, addition of H2 is a cis addition, right? So we get, or syn addition, so we get a cis alkene, right? To make the trans alkene, it's kind of a funky reaction. It's a radical reaction, and one that we're not going to worry too much about the mechanism for. If we had lithium metal in liquid ammonia, right, which again is sort of bizarre conditions. Lithium metal we don't normally see. Making ammonia liquid is a little bit strange, all right, but this is a radical reaction. You can look in Klein to see the mechanism for this reaction, right? It turns out that you can make a trans alkene out of that, right? So we do have ways to turn internal alkyne into a cis or a trans alkene, depending on what you want, right? And clearly you can use these conditions if you had a terminal alkyne as well, right? So if we just had that alkyne, right, you could very easily add H2 and catalytic palladium, and you can make the alkane, right? You could also use one of these other two conditions. Probably Lindlar's catalyst is most popular. And you can make the terminal alkene, right? Those will work just as well, okay? So that's hydrogenation. When we think about hydration and adding water, if we think about the reactions that we used for alkenes, we had three different reactions we used for alkenes. We could add sulfuric acid and water. We could do oxymercuration, demercuration. Those two gave us addition of the oxygen to the more substituted side of the alkene. We also had hydroboration oxidation with the oxygen going to the least substituted side. Now the interesting thing about doing this for alkynes is this is going to be, it's going to give us a synthesis of a carbonyl. So unlike in alkene chemistry where you end up with an alcohol, here you end up with a carbonyl, right? And we'll see why that is in just a minute, right? When you do this reaction, and these are generally only useful for terminal alkynes, right? You get mixtures with internal alkynes. All right. So in general, we're just looking at terminal alkynes, right? So we're looking at something like that, right? And so for alkynes, when we do the sulfuric acid and water reaction, right, you'll also often see this with mercury sulfate. So it's sort of a combination of the sulfuric acid conditions and oxymercuration, demercuration, right? And if you think about what happens in this reaction, you're going to end up generating the more stable carbocation, right? That is not a very stable carbocation at all. Water's going to add to that, right? You're going to have a proton transfer, and you're going to end up at that alcohol, right? And this is the point where you should remember that this is an enol, and that enols undergo tautomerization to give you a ketone, okay? And if you don't remember the mechanism for this, right, definitely should be able to write out the mechanism. So that's something that would be useful to practice, right? So again, this is definitely not stable. The enol is not stable. So all of this happens under these reaction conditions. So you're doing an enol to keto tautomerization under acidic conditions, okay? Now, if we think about the other hydration conditions, those are our hydroboration oxidation conditions. And we have to do something a little different on an alkyne because we know if we use the standard BH3, that would also react with an alkene, right? So we're going to have to use a different reagent. So there are a bunch of different ones, right? That one is diisoamylborane. Sometimes you'll see other groups hanging off the boron. So usually you have some sort of large carbon group on the boron with 2 bonds to boron and then 1 BH bond. And that BH bond is going to do the hydroboration that you're interested in. Since this is so big, it'll block the second addition, so you won't get double addition, right? So what happens in this is that we do our standard reaction where it's a syn addition of H and B to the alkyne in this case. This ends up being stable, it stays there. Now you do the second step of hydroboration oxidation, so hydrogen peroxide, sodium hydroxide, and water. So this is the oxidation step. That brings you yet again to an enol, right? Not stable. And under those reaction conditions, you get tautomerization again. And again, you should write out the mechanism, right? And hopefully it's clear. In this case, instead of doing the tautomerization under acidic conditions like we did on the top route, now we're doing it under basic conditions, right? And again, make sure you can write out the mechanism for both of those because they are going to be different, but it's something we're going to see all the time, right? So this is a really nice example of how doing these hydration reactions, you can make either a ketone or an aldehyde depending on which conditions you pick. Very useful for us. Then we can use those in synthesis to continue to make more complicated materials, right? And finally, the alkylation. And again, alkylation, making a carbon-carbon bond, is only possible with an alkyne. You cannot do this with an alkene. And it's only possible for terminal alkynes, the key being that you have that terminal proton, right? And with a strong base, and the base that we're going to use is NH2 minus. Can also use other bases like butyllithium, things like that. We can deprotonate. To form that anion, right? And I want you to think about, why is that anion easier to form than if we did that on an alkene, right? Much more difficult to do this on an alkene. Not too difficult at all to do it on an alkyne. Now we have this very strong carbon nucleophile. If we react this with some sort of primary alkyl halide, in this case I'm showing a primary alkyl bromide, we can do a substitution reaction, right? So we can do something like that where the alkyne substitutes for the bromine. Br minus is a very good leaving group. So we would get a substitution reaction. And this is a really nice example of the sorts of reactions we're going to start studying in Chapter 7, SN2 reactions, right? Substitution, nucleophilic, bimolecular, right? A great way to make a carbon-carbon bond. And this is the most important reaction of alkynes because it enables us to grow the carbon framework of the molecule, all right? So think about why this is possible, right? Think about and draw out those tautomerization mechanisms. And then on Monday in class, we'll spend some more time talking about applications of alkyne reactions.